Hello together, this is Jonas and I will present joint work at TU Dortmund University with Robin Lange, Jonathan Flossdorf and Carsten Jentsch about detecting changes in topics using rolling LDAs. First, I want to motivate our research. It builds on the intensively researched field of narrative extraction, and to extract narratives from text data and make them interpretable, often entity recognition is applied in combination with other NLP techniques. Our approach is based on topic modeling to create some kind of hypertopics for our narratives. And the idea is that narratives are subtopics in topics from topic models. The shift in word usage in one of these topics can then be interpreted as a narrative shift in, for example, news media coverage. So through topic models, we are first able to determine some kind of a topical localization of a narrative, the hypertopic. In the next step, we want to determine the lifespan of the narrative. We can think of this as the time between narrative shifts, so between changes in the same hypertopic. This would then be the temporal localization of the narrative. And to be fair, we do not think that we solved both problems with our proposed approach completely, but we rather think that we made the first step so that our work can provide groundwork for further research on narrative extraction and interpretation. We make use of topic models for this approach because their idea is straightforward. A set of text is clustered into topics, whereas each text is seen as a mixture of several topics, and each topic is in turn characterized by its word distributions. This is fairly near to a human understanding of texts. In 2003, LDA was introduced by Bly and others for use on text data and has since been cited over 40,000 times. In this unsupervised model, we first think of a collection of texts as a corpus. Here, each text consists of so-called word tokens, WNM, and all these tokens are understood as a bag of words within the text, so the order is not taken into account. To each of these word tokens, the model assigns a so-called latent topic, TNM, where the user specifies how many topics there should be, denoted by K. Due to the property of LDA that a single word at different positions in the same text can be assigned to different topics, it is specified as a soft cluster algorithm, as we do not get fixed classifications per document. And there are three important hyperparameters for LDA. In addition to the number of latent topics, the user must set the Dirichlet parameters alpha and eta, which control the shape of the distribution for texts and topics. So their larger values result in approximately uniform distributions, while smaller values lead to less topics occurring very frequently, or analogously to less words representing one topic. As we do not simply apply LDA, but an enhanced version of LDA, I will explain the idea of rolling LDA, which is a modification of LDA my co-authors and I proposed in November at EMNLP. The idea is to sequential model the whole bunch of text, so we split our text in discretized chunks of text based on their publication date, and in doing so, our model offers the ability to handle new text and update the topic structure based on these. The advantage in comparison to simply calculating a new standard LDA is that the assignments for older text remains the same, so that we get the ability to create consistent time series. So maybe you want to ask why we do not simply add the new text by predicting the assignments using the complete model. We do not do this because it would result in too rigid topics. We want to allow for small changes in topics by preserving the overall topic structure of the hypertopic. As I will illustrate the modeling idea on the dataset used later on, I will also explain how to choose the hyperparameters of this modified LDA. So let's come to our idea of change detection in topics. This kind of detection is always somehow a binary task, so that you can think of multiple tests applied for each topic at each potential timestamp for a change. To perform this test, we calculate the real similarity of the word count vector at the given time point in comparison to the word count vector of previous time points. Then we want to compare this similarity with the so-called expected similarity if we assume somehow stable conditions for this topic. This is the crucial part because news media coverage is to some extent always subject to changes, which is the nature of news media. And for this reason, we try to simulate a number of semi-stable conditions and compare resulting similarity values with the realized value, so that only extraordinary changes are denoted as real changes in topics. Okay, let's begin with some formula. Assume we look at one topic denoted by K at one specific time point denoted by T, and we want to know which changes were detected until this time point T. Then CTK gives us a set of these changes. For this, as explained, we calculate the similarity, here cosine similarity, of the word count vector at the given time point in comparison to the word count vector of a longer reference period. The maximum length of this reference period is selected by the user, so it's one of the two hyperparameters of the change detection method, but the reference period is never longer than the elapsed time since the last detected change. So the similarity of these two guys is then compared to the threshold we still have to define. And don't be confused, the 0 is just included in the set of changes for technical reasons, so that the maximum of CTK is well defined. Okay, now how can we determine QTK and Zmax? For this, we first need to take one step back, because we need to define our semi-stable condition for the topic to be able to say what is our least acceptable similarity without reporting a change. For this, we define the expected word distribution as a mixture of the estimated word distribution at the current time point and the estimated word distribution over the reference period. The estimators can be computed really straightforward based on the word count vectors referring to Griffiths and Stevers. So here we have our second hyperparameter named P for the change detection algorithm. And in my eyes, this is the more important one. Now, using this expected word distribution for topic K at time point T, we resample for a number of times expected word count vectors with the same cardinality of our realized word count vector at the current time point. Then, for comparison to the realized similarity, we use the 1% quantile of the similarity values resulting from the resampled word count vectors. And this procedure needs to be repeated for all topics and time points. This is all about the mathematics, so there will be no more formula from now on. Instead, I will briefly explain which data we used and how we set the parameters to present exemplary the results of our method in an analysis section. So we used the data set proposed by the organizers, TLS COVID-19, which contains articles for 4 different newspapers, Observador, Publico, Guardian, and the one on which I will focus for the presentation, CNN. This subcorpus contains of around 27,000 live blog articles from CNN published between January 22nd in 2020 and December the 12th in 2021. So we applied common NLP preprocessing as stop word removal, number removal, tokenization, changing words to lowercase, and also include lemmatization to resolve word flexion and to aggregate all the information in the word's standard form. Regarding model parameters, we will have a look at the results for 12 topics. We also create models with 8 to 20 models, which can be accessed under the corresponding GitHub repository, but I will focus on 12 topics for today. For the rolling LDA, we assume weekly chunks and in the same sense treat the previous week as so-called memory. And to guarantee reliable results based on the sufficient stable initialization, we use LDA prototype for the first 10 days of the corpus. For the change detection algorithm, we look at Zmax equals 4 and P equals 0.85. But you can have a look at analysis for other parameters values in the repository as well. Just to briefly explain the rolling approach of the modeling procedure, I like to share this flowchart with you. As explained, we model the prototype on the first 10 days, where 605 texts were published in this time period, and then each of the orange bars represents one modeling chunk, and the blue bars to the left of each orange bar represent the corresponding memory, which means the 7 days before. This means that there is no direct information about topic structure for articles in January 2020 if we model the texts starting from the 8th of February. And this is how it's done for all following chunks. Some word about the evaluation procedure we applied to somehow give you an insight on how well the model performs on the task of detecting changes in topics. So to disappoint you, in the first instance, I want to be honest that an extensive study on the model performance is pending, because it would be rather difficult. What we did is we got the set of changes per topic and calculated for the mentioned parameter setting the precision of the detected changes in an, let's say, human-assisted manner. The person who did this had to check plausibility of all changes based on eyeballing. That means that he got the timestamp, external knowledge about the course of the pandemic, the time-dependent top words of the corresponding topic, and word impacts, which we will see on the slide after the next. Unfortunately, we did not find a cheap way to determine a reliable recall value on this dataset, so we postponed this to further research. But of course, we would be happy if there's someone who's able to share a dataset with reliable, so to say, target variables with us, and in particular for this special setting, right? Now we come to our example analysis, which includes monitoring of topic similarities and the word impacts on the next slide. Here we can see the 12 different topics labeled with its top 5 top words and the corresponding realized similarity of the topic's word count vector in comparison to the reference period as blue line, as well as a threshold which marks the least acceptable similarity under semi-stable conditions as a red line. Every time the blue line is lower than the red line, this is marked with a vertical gray line, and this results in 78 detected changes in total, from which our poor Kai, who labeled the changes, found 55 to be plausible based on the given information for this time point. We can see that there are a lot of changes detected in the beginning of the pandemic, where the news media coverage was rather turbulent, and the wording really changed fast. When we exclude those changes at the beginning and start our evaluation in April 2020, we got a precision of 78%. You may ask yourself why there's a drop at the end of all these curves and why our threshold mostly also drops at this time. So this is because there are much less articles published in this time, which results in smaller cardinality of the word count vectors and therefore a higher uncertainty of the observed words and topics. This was an intentional side aim to not detect changes in topics that just come from too less data. To detect those changes, we could simply look at the number of words assigned to each topic over time and would detect this. Finally, I want to show you these fancy word impact plots, where we illustrate the impact of each word at a specific time point on the realized topic's cosine similarity. Technically, we calculate these impacts as the difference of the actual similarity and the similarity if we would neglect this specific word. And in doing so, we get so-called leave one out cosine impact values for each word. We also add the number of absolute occurrences of the word in the topic in this specific week in the plot, and the color of the bar represents whether the word increased or decreased frequency to the previous reference period. And as you can see, there are two different, very different examples here. The first comes from the event that AstraZeneca published a new study about its efficiency, and the second covers the news of Trump getting recovered from COVID. Well, the first is mostly driven by a decrease of the frequency of the word variant more than by the increase of the words like trial, AstraZeneca, and efficiency. The second instead is mostly driven by the huge increase of the word frequency Trump, but also president, test, and negative. So using this type of figures, it seems easy to get an insight of what's going on in the topic, so what kind of narrative shift is in there. I think there's a lot of potential, especially in the visualization of those changes, and so this will be one of our further research projects. But first, I want to share the link to the GitHub repository where you can find a lot of additional material as well as the code for the method and so on. And then I also want to add that we want to improve our evaluation procedure and further research, which should include comparison to other methods, which probably need some slight modifications. And then we want to proceed on the more bigger picture of narrative extraction and determination of their lifespans. Thank you for your attention. And now I'm open for questions and comments.